I don't know how many people are going to come, that type of thing, but generally the way that this will work, if you, yeah, so if you have any particular questions over any of the material that we've ran, like that we've covered for the term, I can go over that, including going over like old assignments, the practice problems, questions on the practice finals, that type of thing. And if it so happens that no one has questions for much of a time at all, then I can start doing a broad level overview just by talking about these topics here. I don't have anything in particular planned out, so yeah, just go over any of the material that's here, and if people have questions as I cover it, we can discuss that from there. So kind of an informal review type session. And yeah, feel free to interrupt at any point in time. And if anyone has any questions, we can use that as a starting point. Oh yeah, I'm definitely going to wait a little bit to see if people join. Yeah, but yeah, either way, it's going to be recorded and uploaded to Learn. So if something does get missed, then we can, well, then people can go back and watch something if they join later, that type of thing. So just while we're here, are there any general topics out of, actually, that's probably the best way to cover it. There we go. Any general topics out of these categories that anyone has a question on? Just so I can kind of get a eyeball of what would be the best thing to give an overview for. So for the focus of the exam, it's about 30% of the stuff before the midterm and 70% after, like 30-40% on the stuff before, somewhere around there. Yeah, so in one of the final exams that was given, uh, they didn't do as much stuff with the combinatorics discrete probability stuff at the end, and they went into more detail on some things for relations and that type of thing. So for one of the two finals, I don't recall which one it was, but for that offering, it seems like 2/3 for the earlier material for our course, but they did cover more material for the first half of the course. So yeah, starting to get populated a bit. Watch this be, can you go over number 3 for the first one? I haven't looked at the answers yet. Yeah, so I will pull up the answer guide for it as well. So, oh, I've been pointing at my screen and I never was sharing it. Okay, yeah, that's a good thing to note. Okay, so if I just pull up the solution key for it and well, it's a good thing. Well, here I was going to turn off the screen sharing just in case I accidentally opened up the wrong file, so I don't show you the final. But yeah, so it was number 3 on the first test. Let me see. That's a lot of space for question 1, 2, 3. Okay. It's okay, show it to me. No, we definitely won't show it beforehand. It's always nerve-wracking when you go to upload, or when, at least for me, whenever I go to upload the things for the final, I always second guess, like, am I uploading the correct file? This doesn't have the solutions. Okay, good. Okay, so for question 3 here, I have the question here and then the solution. So you have a basket of a mixture of apple, oranges, and pears. So in this context, they're just reminding you of what a multi-set is. So yeah. So for example, if you want to pick 3 apples and 2 pears from the basket, you could represent that as a multi-set of this form. Oh, so in order to get the link so I could send out a link to the chat session, he got invited to it. So it tries to pull him in, but he never actually fully joins. So yeah, that's why he was here. Anyways, so for here, they're just reminding you that multi-sets are a thing. And this multi-set would be different from this multi-set because this one would be the case where you grab 3 apples and 2 pears versus grabbing 2 apples and 3 pears. So Alice always picks 3 pieces of fruit from the basket in such a manner that all the multi-sets of 3 pieces of fruit are equally likely. So this is building up by telling you that when she selects 3 pieces of fruit, she does it at random, such that you have a uniform probability distribution over the set of all multi-sets of 3 pieces of fruit. So physically, this could be, for instance, having all 3 apples, or say 1 apple, 1 orange, 1 pear, or all 3 pears, those type of things. She then chooses 2 of them in such a manner that all the multi-sets of size 2 from her 3 are equally likely, and then hands them to Bob. So this is setting up, the first sentence for this question is setting up my sample space, and then she's, from this larger sample space, sampling to pick these 2 sets of, two sets of, well, 1 set of 2 fruits in such a manner that it's this uniform distribution from this bigger sample space. So now we have some probability questions. What is the number of different possibilities for the multi-sets of 2 fruits that Bob could end up with? So here, this one you could do pretty much by brute force if you wanted. And then the second one is what's the probability that they end up with no apples? So here, for this question, the way that you should tackle it, brute force is honestly a pretty good approach. I don't know if they did something more clever than that. Let me, where are you? 2, 3. Yeah, so here, instead of doing the brute force, they just computed them using that. But this is a pretty straightforward version of doing your multi-select type thing, since here, these apples, oranges, and pears are assumed to be like this infinite collection of apples, oranges, and pears. So from there, if you want to compute the number of different possibilities for what Bob could end up with, you just need to compute the number of ways that you can select 2 fruits from this collection, right? Because Bob is really only working in this collection of the 2 fruits. And then for the probability that they have no apples, you just want to compute what are the number of multi-sets that Bob would select that have no apples in them. So yeah, there it's your standard multi-choose formula. So there's 3 of these fruits that you could grab from, and you're picking 2 at random, and then you could just compute that. This form here is the one that I would kind of naturally think of, but this does simplify to the 4 choose 2, which you could also use the stars and bars method indirectly to get to the 4 choose 2 answer if you wanted. And then from there, you need to compute how many of these don't have apples in them. And this is a small enough of a problem that you could, that you could brute force it, but it's just kind of one of your standard going through the little steps. So I can go through this in detail to chase it out if you want, but the kind of TLDR version here is you want to forcefully make Bob pick a setup where there are no apples. So there's multiple ways you can split this up. You could straightforward go out and ask the number of ways that Bob can select something without apples with no extra information. Or you could do the method that they do here, where they split it up into 2 cases, where Alice has apples and then break down the various cases. Like if Alice has no apples in the sets that she selected and handed over to Bob, then in that case, you can compute the number of ways that Bob can select what was remaining out of the things that Alice gave him. Or you can then say, hey, what if she selected 1 apple? And go through those possibilities from there. So doing this breakdown here is kind of the easier way of doing it. Honestly, if I were approaching this problem from scratch, I would probably just do it via brute force for the second half, because it's not too bad to brute force. The numbers are small. So yeah, that would be my kind of version of doing this. And the key idea there is multi-choose, because you have this with replacement going on. It doesn't explicitly say replacement anywhere in the problem, but it's implied with the way that it's set up. So there, I would, like, if I was a student at this point, I would probably would ask just to make sure, like, hey, is this basket actually contain arbitrarily many apples, oranges, and pears? Just for clarification there. Uh, but in the final that you guys have, I was very careful to try to avoid those type of ambiguities there. Okay, so we've had a few more people join throughout there. Are there any questions over any of the material of any of your assignments, anything like that? If not, what I'll do is I can start at the top here and go from top to bottom and just give a high-level overview over all of these topics and kind of highlight some of the things that you should know. Yeah. So with relations, do you want to go over relations in general or binary relations in particular? So the thing with focusing on what is on the final is all of this stuff is fair game for the final. So you should know all of these topics going in. Some of them might not be explicitly, well, there's 6 questions, so some of them won't be explicitly tested on, but you should know everything. So I won't do a keyline focus on only the things that are explicitly covered, but that's just because you should know everything on here. So for relations, if I start with relations in general, so binomial theorem. Yeah, so I will start with relations and I'll do the binomial theorem stuff. So generally speaking, if I want to talk about relations, just kind of in the most abstract sense, it's kind of a generalization of a function, right? So with the function, you have a mapping between 2 sets. So you generally can draw this with the 2 little circles and indicate your elements in these 2 sets. And you can draw these little arrows. But functions had the extra rule that you have to have an arrow going from everything in this set over here. And you can't have 2 arrows going from one object to 2 different objects here. So in this case, that would not be okay for a function. Relations basically just relax this second term here. So that's kind of the very quick TLDR of relations, is that they're just a subset of A cross B, where A cross B are these 2 sets. So in terms of binary relations, when you're talking about a relation between only 2 sets, so something similar to what I wrote up here, you call that a binary relation because there's only 2 sets that you're considering. So in terms of binary relations, you can go back through and redefine your domain, codomain, image, range, all of this good stuff here. That has the standard definitions that you'd expect, and I will go to the what week was that? Maybe 6. But I will go to that to pull out some things. And beyond there, you can talk about special types of relations. So these symmetric, asymmetric, antisymmetric, reflexive, irreflexive, and transitive, these are all properties that a relation can have on a particular set. So in particular, when we talk about these relations, or these type of binary relations, we talk about a relation from a set to itself. So let me just pull up the slides over that. Combinatorics, that's past there. So the main thing that you should know for these type of, yeah, so that'll be good. There we go. So the main thing that you should know on these binary relations is, well, one, what is a binary relation? That's pretty easy. Being able to compute the domain, codomain, range, image, and inverse image. So there's a few examples of that here. Well, this is the definition. You basically just apply these definitions to chase it out. But there's a few examples of that here that if someone wants me to, I can re-go over. And outside of that, you really would want to know, like, how can I determine if a binary relation has one of these properties? Go over these examples. Yeah, I can do that. So here, if G is going to be this subset of R2, so since G is a subset of R2, G would be a relation from R to R. So it takes something in the first component that's a real number, and it relates it to something in the second component that's also a real number. So G would be a binary relation. And here, prove that this is a relation. So that one's going to be basically the argument that I just said, and give its domain, range, the image of this, and the inverse image of this set. Okay, so clearly it's a subset of R2, right? And thus it's a relation. That's what it means to be a relation. Oh, yeah, you can unmute to ask a question. Yeah, so you can unmute whenever you want for that. Okay, so while we're waiting on there, and then if you want to find, where did I do its domain and range? Yeah, so the domain of this will simply be the collection of all the things that can go into the X slots. So here, since this relation X comma Y is the relation where X is greater than Y, if I pick arbitrarily small, as in like very large negative numbers for Y, I can then allow myself to put any number in for X that I want. So from there, the domain of this would be R. And similarly, if I pick any arbitrarily large number for X, that will allow me to put any number in the second slot for Y. So that's where I get this range. Okay, so go ahead for your question.
Hello. So I had a question about relations, and like, let's say we were to prove that it was partially, like it was a partial order or a strict partial order and whatnot, right? Does that mean we have to prove all three cases? Like, you know how I forget
Yes.
exactly what it is.
Yeah, so for all of these, if you want to prove that something is, say, a partial order, then you need to show that it's, well, a relation that basically comes for free, but you need to show that it's reflexive, anti-symmetric, and transitive if you wanted to show it's a partial order.
So, sorry.
Yeah, if you want to disprove that it's not a partial order, it's sufficient to show that one of these doesn't hold.
Okay, good. Because in the solutions, they do all three. But if I do
Yeah,
one,
so in the solutions for that, I did all three just to be complete, but you only need to so if you want to show that something is not a partial order, by definition, you need to show that it is not reflexive or anti-symmetric or transitive.
Oh, okay, I see.
Right?
All right.
So you just want to prove the negation's true. So yeah.
Okay, thank you.
I just did the extra there to be kind of more complete. Okay, another thing, so here if I want to compute the image of the set 1, 2, this is one that I had a handful of questions on. So here, what this is asking is, what are the values, like what is the subset of R, such that if I take those numbers for R and plug them into this slot of the ordered pair, this inequality would be true for either 1 or 2. So literally plug in 1 in here for X, plug in 2 in here for X, and then write down the collection of all of the values of Y that satisfy either of those inequalities. So that's what I do here. So note this thing is the set of all Y and R such that Y is less than 1 or Y is less than 2. So if I put these two inequalities together, I can simplify this to simply the inequality that Y is less than 2. So from here, the image of the set 1, comma 2 under G would be this collection here, or simply that half open interval. So similarly, if I want to find the inverse image of a set under a given relation, I then just want to take the numbers and plug them in for Y instead of X, and go from there. So here, the inverse image would thus be the set of all x and r such that x is bigger than 1 or x is bigger than 2. So if we consider more than one element, it would be the union. Yeah, it's the union of all the ranges of the outputs. So here, in this case, the union of these two cases simplifies to simply be this half open interval here. So all the real numbers greater than 1. So that's what you would get here. Yeah, so this is basically just a generalization of saying like g of a single number. Like, what are all the things that get, or for instance, if I wanted this term here, what are all, if I did this and instead of saying the set 1, 2, I just said the element 1, so g of 1. If this is a function, you would say, what does 1 map to? But since it's a relation, you could say, what are all of the elements that 1 maps to? Since you no longer have the uniqueness there. You could have bifurcations. So that's the basic idea codomain of it. And here, this extra note here is just saying like, hey, it is a binary relation on R2. And this G relation is the same thing as the greater than symbol that you're used to doing. It's just a formal definition of what you mean by greater than. In some sense, it does explicitly require you to define greater than to start with. So it doesn't really define anything new because I'm already using that definition there. But this is one way that you could define the greater than operation. Instead of doing this, you just try to quantify this in words. So yeah, this is basically doing the exact same thing, but with a new relation equals. I don't know if it's worth going into the details here. If someone wants me to go through it, I can. But it's basically the same process that you did here, just with equals instead of greater than. And here, this is yeah, just asking for the domain and range. And it is let A be a set and let S be a subset of this. Yeah, so it's just the subset relation. Okay, so outside of that, if it asks for the codomain of it. So did I explicitly define codomain here? Yeah, so codomain for all of these is just the set that you're mapping into. So the codomain here would just be the R squared, because that, or sorry, R, because that's what you're taking elements from. The codomain here as well would be R, and the codomain here, well, this is mapping from the power set of A to the power set of A. So the codomain would simply be the power set of A. So generally, if you're asked for the codomain, you take the biggest set that you're mapping into. So yeah, and generally another question that I had is what's the purpose of the codomain when generally you care about the range? So if you go back to linear algebra, sometimes if I gave you a matrix, you don't necessarily always know what the range is going to be immediately, and it can be a pain to compute what the range is, right? You need to see what can things get mapped to under this, well, in that case, a matrix, but in general, under this function or this relation. So dealing with the codomain allows you to very quickly define a function or a relation without worrying about the details of, is this actually the range and all of that stuff. So it's kind of a, in practice, you really care about the range more for most problems, but having the codomain is what you first start out with before you go to explore the function more. And there are some useful theorems in terms of codomain stuff, but generally the range is easier, or not easier, but nicer. Okay, so I'll go on to examples of relations, like just this little, actually, that one. Yeah, I can go through this and then talk about the symmetry stuff, unless other people have other questions. Okay, so here, all of these are going to be relations on a set A, just as examples. So the null relation is a very important relation for thinking of counterexamples, generally speaking. So it is a relation. It's trivially a relation because it's trivially a subset of A squared. And it does work nice. I used it here to give some examples of where things can act differently. And generally speaking, the null relation is a good counterexample for some cases. And in some theorems, for instance, where do I do it? Yeah, here I explicitly need non-empty for this theorem to hold. So it can be a kind of edge case you might need to worry about. So if there's any questions regarding relations and things like that, always just keep the empty relation in mind. Okay, so then here, just the equality relation. So if A is related to A, that's the same thing as just your standard equals. U, so if you take the whole set itself, that's a relation, like trivially, a squared is a subset of a squared. And again, the universal relation is good for doing some counterexamples for certain type things. So just keep that in mind if there's a question on relations. This restriction of a relation to another set is quite useful. So yeah, it's just another way that you can build new relations from starting with one relation. So yeah. So here, in terms of these definitions, really, if there's any questions asking about these things, you pretty much just have to appeal to the definition. So if I asked you to show that something is symmetric, or like if this is symmetric, is it also asymmetric, or some type of questions like that, uh, what you would want to do is just basically appeal to these definitions. So it's symmetric if for all points that you can give in x squared, if x is related to y, then y is related to x in the opposite way. So x is related to y if and only if y is related to x. So there are 6 questions and there are some sub-questions. So I know people generally care about that. So 1, 2, 3, 4, 5. So for the first one, there's 5 sub-questions. Don't let the number of questions worry you there. They've been balanced to be normal type final. For 2, there's 4 sub-questions that are all kind of semi-related to each other. For 3, there's 2 sub-questions, but really it's basically one question. So yeah, and then 4 has 1 on its own. 5 has 3 sub-questions that, yeah, and then 6 is just 1 on its own. So if you count the sub-questions, we'd have 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16 if you wanted to count all the sub-questions. But it's not, it might not be, but the sub-questions aren't, it's designed for like 2 to 2.5 hours-ish. So in terms of what it took me to go through and do them on like a little practice thing of coming up with them, I came up with the questions before I did it, so it's kind of unfair. But it took about 15 minutes for me to go through it afterwards. And I did send it to the TA for approval on it in terms of difficulty, and they said it was pretty well balanced. Well, so the other thing is I came up with the questions and then I did the final, right? So I've built the solutions like a week ago, and then after not looking at it for a week, I resat down at it. So they kind of were out of my mind for a bit, but still. But no, generally speaking, the questions that have more parts to them are kind of the easier questions. So yeah, it's not bad. Should have sent it to Zach. Well, Zach would have put multi-select in. Do you want multi-select? But no, it really isn't as bad as it sounds when I talk about all the little subparts. But yeah. Okay, so back to here. So if you wanted to prove that something's symmetric, you basically apply to this definition. If you want to apply that it's anti-asymmetric, you need to show that for every single point x comma y, if x is related to y, then y is not related to x, etc. There are no multiple choice. There is no multi-select. There's nothing like that sitting around there. So it's just 6 main questions, of which some of them have multiple parts. And of the ones where they have multiple parts, some of the multiple parts are decently related to each other. Other ones are just do this problem, do this problem, do this problem. They're all similar in nature under there. So number of little parts, I think I said 19, something like that. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, sorry, 16. Yeah, 16. 16 questions if you count all the subparts as being individual questions. But to that as a metric, let me just go to the midterm. If I open up the midterm, so here you can note that this term had multiple parts to it, and this had multiple parts, and this had multiple parts. Here, these were kind of unrelated to each other, just doing different proof techniques, and you essentially have proven them. And then these other two, like these are unrelated to each other, but once you do one, the other one's kind of similar. And then this one is just holding your hand through the problem. So, you shouldn't lose marks if you sneeze and forget to write a 3. Let me just check to see if I wrote it. I'm joking, but let me just check to see if I wrote a 3 somewhere. Oh, no, I did write some 3s, so no. So part marks will be similar to what it was on the midterm and everything else. Some of the questions are either you get them or you don't to some extent. Just like I don't see for some of the questions how you could get easy partial marks unless you're going in the right direction and then just make a mistake. The whole thing's out of 35, and the points are relatively spaced out. 5, 8, 5, 4, 8, 5. So how hand-holdy are they? Not super hand-holdy, I would say. Like, yeah, in some of them, I hold your hand like, hey, compute this thing, and then in part 2, you need it a little bit, that type of thing. But yeah. So if this was on campus, so if this was an in-person final, the difference between the way that it's written now and the way that I would write it then would be I would probably write down the definitions for a couple of the problems. So if you notice, like over here, this one. So here they tell you what a multi-set is in this question. If I were to include this question on a final, I would basically remove this little thing here where I tell you what a multi-set is. And yeah, if I go to any of these other ones, generally whenever you have a in-person final for things like this, they'll do things like recall that these are the definitions of these things. So, so yeah, in terms of like a key thing you should keep aware of, make sure you write out all of your work, all of your solutions. Try to mimic the type of detail that I went into for making the midterm solutions or the other assignment solutions. So if you do that, then your probability of getting part marks if you make some mistake goes up. So you don't need like pages and pages of stuff, but just make sure that if you have a counting problem, explain why you're using that method, that type thing. That generally leads to higher part marks than if you are very scarce with the work that you present and come to the wrong conclusion. Because it's hard to give part marks if someone okay, so if it's complete BS, then so there is a bonus built in. But if it's complete BS, then the probability is pretty low. Like if I see 3 pages of BS when I'm marking, well, one, if I see 3 pages for a problem that you don't need 3 pages for, the first thing that comes to mind is you did something wrong. So there is one mark that is if you do what the question says, you will get the part mark, and I don't expect anyone to miss getting that part mark. So, yeah. So for the weight of the final, what I'm going to do is I will first compute your grade as it is in Learn, essentially, and I'll take that as is. Oh, well, I'll verify that to make sure that it works, but it does, so that's not a problem. And then after that, I will compare that to the other way of doing the marking, and you'll get the maximum of those two. So I will compute your mark using this formula, and then I will compute your mark using this formula, and whichever one of those is higher is the one that you get. Well, so with drawing the cat, it can't be like a horrible, not nice looking cat. It has to be at least the quality of, and I'm joking, by the way, but it has to be at least the quality of this cat. A drowned rat. No, but yeah, so for the final mark, it's I will compute your mark using this, I will compute your mark using this. Whichever one has a better percent is the one you will get. So it really depends on the relative weighting of your midterm versus the final, which one you end up getting. So just kind of keep that in mind there. So outside of that, yeah, these charts might come in handy if like you're trying to figure out things of different relations here. And then the same thing kind of holds for reflexive, irreflexive. You literally just apply to the definition. So if you want to show something's reflexive, check that. If you want to show something's irreflexive, check that. And then some TA would try to expose us. Yeah, so I use AI to check the drawings of the. There is no drawing of a cat, but yeah, you could use AI to check that anyways. But yeah, so in terms of relations, I know it kind of jumped around with everything. Sorry for asking again, but would we get an entire bonus question that's worth this? So you get one question that is worth 1 point out of the 35 that you should be guaranteed to get that 1 point. So at worst case scenario, if you submit it on time and you do everything else wrong, you should get 2.8% on the final. So you basically get 2.8 free percentage points. So, but generally speaking, if you did well on the midterm and you've done well on the assignments going forward and you understand the material, then you shouldn't have problems on the final. It's just kind of taking like a little bit of maybe this or this or this and putting them together for questions. There aren't any questions that are, in my opinion, as difficult as the Pikachu question on your assignment. So my opinion, of course, but so you can kind of use that as a difficulty level for balancing it. We have to put them together. Ruin Pikachu for us. Yeah, so the combinatorics discrete probability stuff, for the most part, has been toned down compared to the difficulty of the assignments. The assignments individually weren't worth that many points, so I could test you on things that were, I mean, easily something that I could have put on the final, but things that are a bit more involved, just so that you have to digest the material a bit better. But yeah, so there was a question on binomial theorem that was talked about. So literally all of the topics that are on this list are fair game to be on there. And hardest is subjective, but all of the topics on this list are fair game to be on the final. Like I could ask you to do a proof by contrapositive, something like that. I could ask you to do induction. You could have some propositional logic stuff. Sets, that's all fair game. Priest, that's super truth table. Well, technically, everything that we built up is built off of logic. So you could technically prove almost everything in this course via truth table, given that it's finite dimensional. Even if it's not finite dimensional, you could still technically use a truth table. You won't want to do it, but anyways, so in terms of material, it's all taken from here, and any of these topics could be on there. So yeah, actually, I have had a few of the proof is trivial and left to it. They don't get points. Anyways, so binomial theorem with application. So the explanation of binomial theorem is the TLDR version. That's asked earlier, but the TLDR version of binomial theorem is it allows you to expand binomial expansions. Where are you? But it allows you to expand those binomial expansions. And the reason why you would want to know the proof for binomial theorem is mostly so that you can be comfortable with dealing with these combinations and how to add them together and how to do manipulations there. So the proof for the binomial theorem is mostly important just so that you know how to do these type of manipulations. So in practice, being able to do this type of stuff is very important for algebraically solving problems. So that's why you would want to know the proof for binomial theorem. I'm not, well, it's a closed or it's an open book test, right? So, so in terms of numerical methods, I don't know exactly what they cover, but it may or may not. So that's ECE 124. Let's see if I can find a, was it 124? Oh, 204. But anyways, so the main thing that you should get out of this stuff here is the ability to do these manipulations. And the theorem itself, one, it can be useful for computing things. Like if you want to compute a sum of this form, you just use binomial theorem and you're done. And it can be useful for doing the things like over here somewhere where I ask to find the coefficients of a particular term. So these are the types of things that can be useful there. So just looking at 120 or 204, computational number systems, error propagation, it won't have too much to do with the material here. There you're going to be more interested in dealing with the issues that you have when dealing with floating point operations. So for instance, you can add a number to a, you can add a non-zero number to 1, and the answer will be 1 if you tell a computer to do it. Then you'll basically be doing things like Newton's method and other things to solve find roots of equations. Numerical linear algebra, that can be very vague. Yeah, so BT is to be able to solve questions like this and to be able to do these type of manipulations. So the manipulations with the finite sums and the manipulations with these binomial coefficients. Both of those are good skills, and they're very valuable if you start doing much with counting, right? So I've covered that one. 16 if you cover all the parts, 6 net questions. So 6 and then 16 if you count all of the tiny little parts, which some of which build on top of each other. So go with the 6 rather than the 16, at least mentally. But yeah, any other questions on the binomial coefficient stuff? But yeah, so some of the stuff that you covered in linear algebra, that's the things that you'll cover in the numerical methods course. That would actually be a pretty fun course, I think. I've taught similar things at the grad level before. Yeah, I quite enjoy that. Optimization, those type of things are fun. There might be a coding component, I don't know. But in terms of the material we've covered, the only thing that could be maybe slightly related, did it say integration techniques? Yeah, if you do numerical integration, you technically could go through and do, sorry, opening it up. You technically could go through and do these Monte Carlo simulations for numerical integration. Like this is a valid method. It's just what's called non-deterministic. So yeah, you won't cover it most likely. you'll probably cover things like Simpson's rule and things like that. Okay, so any other questions on these materials? So that's what you'd want for binomial theorem and applications. I've covered roughly binary relations, kind of amongst talking back and forth. The 3 different tile types. Yeah, let me open up those in terms of lecture slides for you. So basically, that's all multi-choose stuff. It'll be after that. So basically, you can technically get by pretty much everything without knowing probability distributions, or those particular probability distributions. But it can help you on problems. Okay. So I will have sessions tomorrow, but I won't do things on Friday. So I have the 2 office hour sessions tomorrow that you can ask all of the questions you want then, and that will go all the way up to the one that's in the evening. So you'll have morning and evening for opportunities to ask questions. I think that should cover anything you have there. Outside of that, Piazza will still be open, so you can always ask there. Okay, so in terms of the PDFs that you have for this course, we really have kind of 2 non-trivial flavors, but 3 that I gave you. There's the uniform probability distribution. So this is the one where everything is, the probability of any given event is the same as all of the other events in your sample space. So this works well for fair die, fair coins, things like that. If it's not uniform, we call it non-uniform. So all these other ones are non-uniforms distributions. So a Bernoulli trial is the type of event where you have 2 outcomes, either true or false. So there's many things that you can turn into a Bernoulli trial. Like say if I'm rolling a dice and I want to get a result less than 3, that would be a Bernoulli trial. So it's either less than 3 or it's greater than or equal to 3. So whenever you have these Bernoulli trials, you only have 2 probabilities that you care of. There's the probability P that one of the event occurs, and then there's the probability 1 minus P, and that's the probability that the other event occurs. Since they're complementary, those are the only 2 options. So from there, you can build up this Bernoulli distribution. So Bernoulli distribution is just a fancy way of saying that the probability that x is equal to 1 is P, and the probability that x is equal to 0 is 1 minus P. So it's the same thing that I said just previously. It's just new way to write it. So now this thing here, if I treat x as an indicator random variable, since we now have that terminology, I can restructure this probability distribution function to be a single function without having this case analysis thing going on. So in that case, I could just write it like this. So x is either 0 or 1. If it is 1, this whole thing gives me p because this term's 0. And if it is 0, this term goes to 0, and this thing gives me 1 minus p. So this is just a compact way of writing out the Bernoulli distribution that can be useful for some problems. So in particular, if I go to the biased coin where I was flipping it to try to get a fair toss out of the biased coin, I essentially was using the fact that I could write the probability that things occur in this form here. So that's kind of its strength. It allows you to get away with doing less algebra and just jump to this formulation here, as opposed to doing some algebraic manipulations and save yourself some time. So now with this Bernoulli distribution, I can then, so here's just kind of 2 more examples of Bernoulli distributions. But with this Bernoulli distribution, I can then ask the question like, hey, what if I do not just one Bernoulli trial, but a bunch of Bernoulli trials? You can ask the natural question, how many times will the trial be a success out of 50 runs or something like that? So to answer that is where we go to the binomial distribution. So if I skip over the motivational example for now, the binomial distribution as a PDF would be this function here. So here I get the n choose x, where n is the number of repeated independent Bernoulli trials I ran. So say if I'm flipping a coin 50 times, this would be 50. And here x is the number of successes that I would get out of those 50. And here, just notice that this part here is simply taking is simply the probability of getting P to occur, so this event with probability P happening X times, and this 1 minus P occurring in minus X times. And then I need this combination bit here to account for the fact that there's multiple ways that I can get to the bottom of this little structure to end up at the same combination of passes and fails. So to be a bit more explicit there, if I open you up. So here, say if I wanted the case where I have exactly 2 fails, then you would want to know the probability of this thing plus the probability of this thing plus the probability of this thing, right? But these are uniformly distributed, like, well, not the individual bins, but these all have the same probability of happening. It's going to be P to the first, because I passed once, times 1 minus P to the second, because I failed twice. And there's 3 of these, so the way that I can count these is this binomial coefficient here. So that's why I get this extra term there, just kind of where it came from. So TLDR, if things are uniformly distributed, use the uniform distribution. If you have something that's a pass or fail type thing, has a probability distribution given by this Bernoulli distribution, which you can do of this form or this form. And oftentimes, if you're doing simple problems, you don't necessarily need to appeal to the distribution, but it can make things faster. And if you want to know the number of times that you will succeed in a certain event, given that you have, or succeed a certain number of times, given that you have n of these independent Bernoulli trials that you run through, that probability distribution would be given by this thing here. So yeah, one of these is probably going to be on the final. Like at least one of these will probably be on the final. Like if I'm talking about probability, we're probably going to want to appeal to something between one of these. So extra little hint of material. So you should know this. And going through these examples here could be quite good. Oh, so this PDF is available on, with all the solutions. So no, I won't also send the PDF of the one without the solutions. But if you want a spoiler for the final, such a troll. If you want a spoiler for the final, this is related to one of the questions on the final. So there are cats. I'm not a cat. Yep, and it actually is exactly the one that the Piazza Post was asking about. No, I literally just took a picture off the final. It tells you nothing about it. Well, it's going to ask you something about the cats. And actually, yes, this is the part that does have the one free mark tied to it. That is related to these 3 cats. Yeah, smudge is actually, so if you've probably seen the meme with the woman and the cat looking at the salad very sad faced. Smudge is that cat. And this cat evidently did actually get put. So this one all 3 of these I got off the internet, but this one supposedly had like a actual run for president, kind of a joking run. So yeah, the time is meow. Anyways, so those are these distributions. Looking at the Stardew Valley problem and knowing how to do this would be good. Yeah, I like I like Limberbutt the most, I think. Just the production quality there is nice. But yeah, so looking at these would be good. You don't need this stuff here or the Galton board example. Actually, I never uploaded that. If someone wants it, just tell me and I can upload it. But yeah, and this thing here might be useful as a TLDR version. But yeah, so you definitely should know that. Yep, I've seen Zach's cats. Not in person, but digitally. I have a shrimp. It's did not drop the shrimp. Don't worry, that was just the base. Yeah. Anyways, so with that, the other thing that you could note is I could ask you to do something with expected value, and you all should know how to compute expected value now. There won't be anything for the infinite cases that we looked at before, so there's no infinite series on the final, so keep that in mind. But I could ask you something with like this that might tie into some of the probability distributions. So keep that in mind as another thing that could be on there. Okay, so we've kind of jumped around in and out talking about math things and not. So an indicator random variable, did I ever say number? Because indicator random number isn't standard terminology at least, but an indicator random variable is just a variable that's either 1 or 0. So they are useful because, actually, let me open up your textbook. Ooh, that was weird. Okay, so they're useful because they allow you to shorten some problems. No, so a discrete random variable are the random variables that we have been talking about. So the discreteness is telling you that it's either finite or countable. The randomness is telling you that it's random, and variable is telling you that it's a variable. So from discrete random variable, that is literally telling you that it is a random variable that takes on discrete values. So an indicator random variable is an example of a discrete random variable, but there are discrete random variables that aren't indicator random variables. So for instance, if I roll a die, the result that I get on the die, say 1 through whatever, how many sides I have, that's a discrete random variable. Or say if I go to flip a coin, whether I get heads or tails, that's a discrete random variable. And in that case, since it's either heads or tails, you could say it's either 1 or 0. That would be a discrete random variable that is also an indicator random variable. So that's really the difference there. So anytime for any of these things where I did expected value, yeah, do keep this meme in mind. If you get a probability bigger than 1, something's wrong. But anytime I did anything with expected value or anything like that, so that one is one of the last ones. I think it was week. So technically, you can pass the final, as in like you can get every question correct without knowing indicator random variables or linearity of expected value. But it can help you on one problem in particular. So if I just go here, so here in this case, essentially, you had this problem here with this really long way of solving it. And here's your explanations for little steps. And yeah, so this isn't a nice solution in the sense of it's long. But instead of doing that, if you introduce this idea of an indicator random variable, so it has 2 values, 0 and 1, then you have this nice property that the expected value of x is simply the probability that x is equal to 1. So with this nice property, along with the linearity of expectation, so that's literally just this formula here, you can solve that previous question in this tiny little thing here. So I would suggest going through this example 40. I do it in the video lectures for week 12, or you could just read it here if you can follow it. But I do suggest going through here to be able to know how you can use these indicator random variables, and it could make one of the problems a little bit quicker to solve. Either way, it's not bad. It's just if you do it this way, it's a bit easier, in my opinion. A little bit less work to do, but it does also kind of depend from your perspective, but yeah. So that would be the only thing that you might want for indicator random variables and linearities. Yeah, definitely watch them. You should also get, actually I haven't checked for a couple hours, but you should get your feedback on the assignment sometime tomorrow. TAs we're going a little bit behind, so they'll probably do catching up. Yeah, I'll send the reminder email, but you should get the stuff sometime tomorrow. Worst case scenario, if like everything goes bad, you should get it by Friday just to get your feedback. So yeah, are there any other questions? So I didn't really do the high level overview. So is this a troll ask or a real ask? Today I had wrap that I put grilled chicken and a bunch of veggies in. And a lot of tea. Yeah, it was pretty good. So he actually means yes. Okay, so Bayes' theorem is the most important theorem than this. No, so let me just pull it up. So basically, Bayes' theorem, the basic idea is if you know the probability that a certain event occurs, and then you get extra information that something else happened, and you want to compute the new probability that the thing happened given this new information, that's what Bayes' theorem allows you to do. So the way that you derive Bayes' theorem is simply by taking these two formulas here for this conditional probability and putting them together. Yeah, so it's like rain. So you can say, so it could apply for things like that if you know extra information about the likelihood that it would rain 2 days in a row. But it's more useful for things like, say if the weatherman said there's a 100% chance it's going to rain or an 80% chance that it's going to rain, something like that. That would be, say, your probability of A. The probability that it's going, actually, yeah. So the weatherman says it's going to rain, and he gives you a probability that it will rain. But the weatherman's not always right? Sometimes they're correct, sometimes they're wrong. Sometimes they predict rain, and it does rain. Sometimes they predict rain, and it doesn't, etc. So what you can do is you can take the probability that you expect it to rain tomorrow, given from that forecast, and then you could modify that probability based on stuff you know about that particular weather forecast model or, yeah, that news station, etc. And by using that extra information, you can get the probability that it will rain tomorrow, given that rain was predicted tomorrow. And in general, if you're doing that, you don't really want to use this formula for Bayes' theorem, since computing the probability of B, in this case, that'd be the probability that they predict rain, is not an easy thing to do, right? Like, what's the probability that they predict rain? So instead of computing B directly, you use this expansion of B to compute this term here. So here is the probability that it rains tomorrow, like the percent that you had a priori, this likelihood that you had a priori, and these two bits of information about the accuracy of the weatherman. So the probability that they predict rain when it does rain, and the probability that they predict rain when it doesn't rain. And you just toss it into this formula and you're done. That's kind of the quick TLDR if you mechanically wanted to use Bayes' theorem. And the basic idea is you're taking this thing here and then modifying it based off of information that you know about previous predictions. So it's good for things like that, and it's good for all these vaccination type questions. Or not vaccination here, COVID test questions. So for good practice for the final, I would highly suggest going through all of the old assignments, looking at what your errors were, looking like what you got wrong, what you got right, looking at the most common errors. So that list of what the most common errors were for previous materials, that's very good practice to look at. Like the common errors that were made on the previous assignments realistically are going to also be the common errors on the final. That's just usually how it works. So if you go to learn and look at all of those, the feedback questions, looking at that could be good prep there. So after you've gone through and looked at your assignments, or maybe some of the practice assignment questions, especially if you haven't looked at them before, then I would suggest going through one or maybe both of the finals, trying to solve it on your own. Say, give yourself an allotted time slot of like 2 hours or something like that to try it, and then look up the solution to see if you agree with, like, if what you found agrees with that. That's my tip for doing studying there, is just basically to use the final as kind of a, you did all the studying things to start with so that you're prepped to do the test final, and then the topics that you did bad on or didn't get the solution correct to, or maybe the ones that took you longer to come up with the solution for, then focus on those type topics. So that would be my hint, and the other hint would be make sure you know all of these topics here. So the other finals are relatively indicative of what will be on this final. The key kind of difference is they had more focus on this material up to like here beforehand, and we have a bit more combinatoric stuff. So, okay, so this will be recorded on the video. There's one. Actually, that's so in terms of things that came before the midterm, or the things that were on the midterm, there's, I'll call that a half and that a half. So I'll call that 1 point problem between those two. So I'd say there's 2 problems out of the 6 on the previous material. Like 2 questions involve some of the old material and some of the newish material in some sense. So between those 2, I'd say it's a half on each one. And then the remaining 4 are all related to the later half. So that's my 30-40% breakdown, but a bit more detailed there. So yeah. So out of these topics, actually, these topics here, expect to have roughly 4 type questions of things involving this. So let me just double check that. 1, 2, 3. Yeah. So yeah, basically expect 4 questions on these topics and expect the rest of them to be on these topics. And there is some there are some questions that test both at the same time. So like I could do a combinatorics problem on any of these type things. So that's the easy way, or probability on any of these type things. So yeah. So yes, you can ask a question unrelated to the course, and if you want, you can unmute too.
Hello.
Yep, I can hear you.
So I have a big question, which is I couldn't find the answer to, and I want to see if you would understand.
Okay.
So if 2 people were playing chess, right,
Mm-hmm.
and one person can read the other person's mind, but the
Okay.
other person can see the future, who would win?
Oh God. That might be one of those little paradox things even.
Yeah, like I thought it would be a
Well,
paradox.
so you also have assumptions built in there. Like, is like either of are either of them trying to win? Do they know necessarily chess? Like the one that can read the future could maybe only see the future where they fail, and no matter what they do, they just keep failing. Yeah, I think that's one of the things where you need to box yourself in a bit more. But
Interesting. Okay,
yeah,
I
I
see.
mean, so the fact that the one person can read the other person's mind means that they can see the future as well, because they can see what the other person's in their mind, right?
Yeah,
So the mind reader probably definitely has an advantage because they can see the other bit. But
I don't know. I was just thinking about it, but like every single time I think, it's just a pair. Like I just run back in a circle, basically. You get what I mean?
yeah, like yeah, you'd want to box yourself in a bit more to get a paradox, because there's kind of cop outs. Like, well, the one that's reading it just didn't care, and he didn't want to win anyways. So yeah.
Interesting.
Yeah, but
Okay. Well,
definitely knowing a single move is basically tells you nothing for chess, right? You want to know big overarching type things. Like, hey, you put this piece here, that pins this, but if you don't know what a pin is, then Yeah.
Okay, I see. Okay, cool. Thank you.
Yeah. Those type of questions can be fun.
They're very interesting.
Yeah. I mean, yeah, especially if you end up with the actual paradox out of it.
Yeah. Okay, well, yeah, thank you, bro. Didn't
Yep, no
want to
problem.
interrupt this, you know.
Yeah, it's all good. Do we have any other questions? So, like I said, we have office hours tomorrow, which basically is another one of these sessions, if you will. And then we have another office hours in that evening. So you have plenty of other opportunities to ask questions after you try to digest this a bit more. And Piazza is open, so you can ask any question you want on Piazza. Okay, so yeah, definitely do look over all of these type things. Uh, I didn't get into any of the nitty gritty details on pretty much anything. So power kitten. Uh, so yeah, just make sure you know the definitions and you know how to prove or disprove the things. Yeah, so the stars and bars. So in terms of what's available during the final, it'll be the exact same setup for the midterm. And I will go through the stars and bars as well. But it'll be the exact same setup that you had for the midterms. So Piazza will be open, emails are open. Piazza is better than emails. So if you do an email, you might get lost because I do turn on the thing where Piazza will send me notifications. There's a possibility that you'll get lost in that. So if you want quicker response, send it through Piazza. But it'll be private questions only. Okay, so for the stars and bars method, basically, many questions can be simplified to say, I have a bunch of bins. Will you not let me go over to the side? Because there. Let's just do it over here. Bye, kittens. So you have a bunch of bins. Let's boot that up. And with these bins, you want to put balls in it. So examples of this are the D&D example that I gave for the classes, or another kind of classic, well, classic examples of this are basically anything where you are doing a uh, problem where order matters and you're doing, or where order doesn't matter and you're doing replacement. Uh, so basically, if I wanted to know how many ways could I put 3 balls, these 3 things, into these 1, 2, 3, 4, 5 bins, the way that you could do that is trying to say like, hey, how many ways can I put them in the different bins, which is very tedious, or you can turn this into a combination problem. So if I were to put these balls into the bins, what would that look like? Well, I'd have something where these would look in here, maybe something like this, where I have 2 balls here, 1 here, and the rest are empty. So I can convert this to a string. So in particular, I could say I have a line. Oops, let me make this thicker. But in particular, you could say I have a line. There's nothing here. So then I have another line. Then I have a ball. So let's just put a dot or a star. Then I have another bar. And then I have 2 dots or stars. And then I have these other 3 bars. Well, I don't need the last one. And I also don't need this one. Beep, beep, beep. There we go, right? So I just need this one to separate between these two, this one to separate between these two, this one, and this one to separate those bins. So now, this problem of asking how many ways can I put the balls into these containers is the same thing as asking what are the possible number of ways that I can rearrange this. So the times when you would want to do stars and bars were generally speaking, just going straight to the multi-choose is like once you understand what multi-choose does, then you go straight to it. In terms of doing things from scratch and splitting it up into this thing here and then doing solving this via combinations, you'll very seldomly do that in practice. It's just that's the method that you use to solve this thing. And the other reason why you would want to know the method, it's harder to forget the method. It's easy to forget the formula. for instance, I have my in multi-choose k, right? 3 years from now, or a month from now, or a week from now even, which one is in and which one is k? Where do the bins go and where do the balls go? Questions like that are things that you can forget rather easily, whereas this method is pretty hard to forget once you learn it. So that's why I would suggest knowing how to do it this way and then get to the formula. So basically knowing the derivation. But in practice, if I give you a problem, you could simply say that was of this form. You could argue why this method works, and then you could just plug it into the formula. So yeah. So generally speaking, the should you bother, you don't have to bother, but you should know it at least. It adds a lot to your ability to do problems just by knowing this method as well. So yeah, but that is the quick going over it. Do you have any other questions there, or is that good? And then again, there's the questions, whichever lecture it was, where I did them with the D&D problem that you can look at as well. And I think I did a couple other examples there, but yeah. Okay, so if there are no other questions, that I can shut down and then go ahead and start the downloading, uploading process. So this will, well, for those of you who are here, this will be posted under office hours, and yeah, it'll just be called review session or something like that. I'll probably send out a email in the morning just to do a morning email reminder thing then. So yeah. Okay. No other questions? Let's see if that's just catching up. Yeah, that's just catching up. Questions going once. Questions going twice. Okay, so I'll call that a quit from here and go ahead and stop the recording.